Well, twistor theory is a little bit hard to describe because it's a mathematical theory, but the twistor is more complicated because that's where you consider the spin of the photon. You can describe fields, you can describe Maxwell's equations very nicely in the subject, and you can see where the positive and negative frequencies work. When Einstein first heard about it, he didn't like it at all. It was quite ironic. But later on, it was crucial to his development of general relativity. All these things become nice. It becomes nice geometry. It was nice for me because I think visually, and I like to think of things in geometrical ways.
Because you are geometric.
Yes.
This exclusive interview with Sir Roger Penrose is intended for intellectually adventurous viewers only.
And my first question to you is, how are you?
How am I? I'm fine. Pretty well.
Very good. We had a chance to meet each other a few months ago. We're back here to Oxford to ask you some questions, mostly about the twistors theory. Mm-hmm. So my first question is, what is a twistor theory? It's very, very difficult, but it could change the world, how we look at the reality around.
Well, twistor theory is a little bit hard to describe because it's a mathematical theory which describes the structure of space-time in an unusual way. So rather than thinking of space-time, which is a four-dimensional space, three of space and one of time, and a point represents a moment which has a momentary existence. So it's the basic element of space-time is a point, and then you built it out of the points. Now in twistor theory you take a different point of view. The basic element is not so much a point, but as a light ray. So you think of the history of a photon, if you like, which is a line in space-time. It's a what's called a null line. It's travels at the speed of light, well, light ray would. And if you like, your analog of a point is a light ray. It's actually not quite that, it's more than that, because the light ray is only the trajectory of a photon. The twistor idea incorporates other things like the momentum and the angular momentum of the photon. However, and the spin of the photon. You see, photons have a helicity and a spin. The helicity depends on which way it's spinning, right-handed or left-handed. And when you incorporate the handedness of the photon, you find it's not completely localized. And there is a structure which is not localized along a light ray, but spread out in a certain way. And it twists around itself. And this twisting configuration is the origin of the name, twistor. So that the element has this twisting characteristic. But the original idea of the subject has a sort of complicated history. Let me try and explain it. It came from basically two ideas. You see, when I was, I think it was in 62, I think. I was in Syracuse University. I had done my PhD in Cambridge, and I then went and did some research, mainly at Princeton. And then I was at Princeton on a fellowship for a year and a half, and it was a 2-year fellowship, and the other half of the year I spent at Syracuse in New York State. And I shared an office with Engelbert Schucking, who was a German who'd left Germany just before the war, and he was a very original man who knew everything, and also he knew everything and everybody, and original, which is unusual. But I had discussions with him, and he explained that two most important things, one most important thing of quantum field theory, which had to do with the splitting of fields amplitudes into positive and negative frequencies. It's hard to explain what that means, but it depends on normally where you do it. You do a complicated kind of thing called Fourier decomposition. you spread things into different frequencies, and then you take the positive frequency and not the negative frequency. That's a complicated thing to explain to somebody who's not a scientist. But then the other thing he told me about was the conformal invariance of the Maxwell equations. The Maxwell equations describe electricity, magnetism, and light. An amazing set of equations, and they theoretically explain light, which is an amazing thing. Light was a quite complete mystery before this. And the different frequencies that you have and the ones that we don't see, and all that sort of part of Maxwell's equations. But it described electricity, and it was a sort of unification of these ideas, electricity, magnetism, and light. And the Maxwell equations, another thing Engelbert Schucking mentioned to me, was that the Maxwell equations are conformally invariant. Now, what does conformally invariant mean? That means that it's independent of scale. So big and small are equivalent. People might be familiar with the pictures of the Dutch artist M.C. Escher. And there are pictures which depict a sort of universe with angels and devils in them, and it's all within a circle. Mm-hmm. And then the angels and devils, you get towards the edge, they look smaller and smaller and smaller, but they're conformal. But the shapes, especially small shapes, if you look at the eyes of the devils, you see they're exactly the same shape, even though they get smaller as you go to the edge. So this is what's called conformal. And conformal way of looking at physics was very important to me, because it led to various things. For example, how you talk about radiation and fields, infinity, and you use the Escher trick by bringing infinity to a finite place, and then you can study it just as though it was like anywhere else. So conformal is useful when you're thinking about things which have no mass. You see, photons have no mass, so they're a good thing to think about conformally. Mass adds another ingredient. And it's a little bit difficult to get around to twistor theory, you see, because the idea was to think of conformal invariance.
Because as I understand correctly, in the twistor story, space-time points stop to play the main role, the basic role, for occurrence of physical phenomena. Space-time points are secondary construction,
yes,
and the primary is twistor.
Yes, well, think of them as light rays, but the twistor is more complicated because that's where you consider the spin of the photon. See, when it has spin, it's not localized, and it becomes spread out to some degree. And the way you can describe this in terms of this twisting configuration, and I had a nice way of describing this, and the advantage of this, I should go back to the other story, was to describe positive and negative frequencies in a conformally invariant way, because the normal way people do it, it's not conformally invariant. It depends on the metric. But for electromagnetism, I wanted to have it conformal invariant. So how do you describe that in a nice geometrical way? And this was the origin of twistor theory, because the original thought, it's quite hard to explain these things without being a little bit technical. But let me just explain. There is a structure called a Riemann sphere. Mm-hmm. You see, you have to think first of all of complex numbers. Now, a complex number involves the square root of -1. You see, in ordinary mathematics, you think of real numbers, and the square root of a real number, a positive real number, is another number. But if it's a negative...
Here the idea is to use complex number instead of real numbers.
Yes, the complex numbers are absolutely fundamental. You see, they're fundamental to quantum mechanics. The whole structure of quantum mechanics depends on complex numbers. The wave function of a photon, the wave function of any system, is a complex number system. So when you think of the Schrödinger equation, which talks about the evolution of a wave function, this really is a complex equation. So in order to understand the physics of quantum mechanics, you need to understand about complex numbers. Now, complex number is called complex because it's not simple. As I say, involves not only a real number, but an imaginary, what people call an imaginary number. We don't like to think of it as imaginary in mathematics because it's just as real as a real number in a certain sense. But you can't see it so directly. You see the way that a ruler measures in one direction, and it measures in terms of real numbers. But a complex number involves a real number and an imaginary number together. And it forms a very beautiful algebra and calculus, which sort of extends from the ordinary algebra and calculus of real numbers to the complex numbers, which are essential for quantum mechanics. Now, you can understand this problem of the positive and negative frequencies very nicely in terms of complex numbers. See, basically it says, you have to think of the complex plane. The complex plane, or the Wessel plane, I guess it was Wessel who first thought of it. People call it the Gauss plane sometimes. Gauss was probably a little bit later than Wessel. Usually he was before everybody else, but in this case I think he was a bit later. Then you sort of have a picture where you have the real numbers going off along one axis, and then the imaginary numbers involving the square roots of negative numbers. I is the square root of -1, and then the multiples of I go up in one day, and the multiples of -I go that way. And you have a plane. So all the complex numbers are represented on this plane. A point on that plane represents a complex number.
Twistors arise from mathematics of complex number.
Yes, very much so. It's absolutely crucial to the subject. And the idea was to make the fundamental principle of quantum field theory, which is to split your fields into positive and negative frequencies. So you do this in a nice geometrical way, rather than talking about the Fourier decomposition, which is a bit complicated. And it does it in a conformally invariant way. So you could talk about the physics being conformally invariant, which I should say really applies to things without mass. When they have mass, then it's more complicated. But originally, twistor theory is concerned with things without mass. So then you can talk about the positive and negative frequency very nicely, because, you see, what I was trying to do, it's hard to explain these ideas because they're very mathematical. You see, you have to think of how you describe this notion of positive and negative frequency. In one dimension, it's quite easy because you think of the complex plane, and the functions which extend into one half are positive frequency, and the ones which extend into the other half. When I say one half, I mean you have the real axis, and then you've got one half of the complex plane goes up, the other part goes down, and those functions which go up are the positive frequency ones, and the ones which go down are the negative frequency ones. So you have a very nice picture of positive and negative frequency splitting in this geometrical way. Now, how do you do that for the full four-dimensional space-time? See, that's just one dimension. If you're talking about one time dimension, that's fine. That's a good picture. But if you want to talk all together for space-time, how do you do this for space-time? Well, you can make space-time complex, but that doesn't help too much, because in this complex, you have an 8-dimensional space. You see, each space dimension becomes 2. Each time dimension becomes 2 again. So 3 space dimensions become 6. The 2 time dimensions become 2 more, and that gives you an 8-dimensional space. And how do you see in this 8-dimensional space how to split functions into their positive and negative frequency? It doesn't work anymore because your real space doesn't divide it in 2 halves, because it's only 4 dimensions sitting inside an 8-dimensional space. That doesn't cut it in 2 halves. It's just a little 4 dimensions is a tiny little sliver in this huge 8-dimensional space. So to try and do this splitting in a nice geometrical way the idea I had was to say, you don't think of points, you think of the light rays. And the light rays in space-time form a 5-dimensional space. Now, the twistors involve the light rays which spin round, so that you think of the photon having angular momentum as well, or spin, you see it has a spin. Yeah. Then they incorporate the other dimension, and so you get 6 dimensions. So you have the space, which is the twistor space, which is 6-dimensional, and this does split in 2 halves, because the real light ray space is 5-dimensional, and the space of the twistors, these are what I call projective twistors actually, but never mind about that. This twistor space is 6-dimensional. So 5 does split it into 2 halves. And so the ones which go one way are the positive frequency, and the ones that go the other way are the negative frequency. And so this gives you a very nice geometrical way of thinking of this key property needed for quantum field theory. And that was the original motivation of twistor theory. Now the subject has got developed in much, much more complicated ways, and you can describe fields, you can describe Maxwell's equations very nicely in the subject, and you can see where the positive and negative frequencies work and make it quantum mechanical, and all these things become nice. It becomes a nice geometry. It was nice for me because I think visually, and I like to think of things in geometrical way.
Because you are geometry.
Yes, I think very geometrically.
On the website of the Columbia University,
yes,
there is this sentence about you and twistor theory. His work on twistors is the most important new idea about the space-time geometry post-Einstein, and we believe it will be studied long after string theory.
Well, I hope that's true. You see, string theory, the main trouble with string theory, in my view, is that it's not very carefully focused on the dimensionality of space-time. Originally, the idea of strings quite appealed to me when I heard about it. But then when they said, it only works in 26 dimensions, so, okay, well, that's the end as far as I'm concerned. That's the wrong number of dimensions. Then they got it down to 10 dimensions, which seemed to be an improvement, but it's a long way along from the 4 dimensions we need for space-time. So I didn't get very excited about twistor theory. When I learnt it, you had to do it in 10 dimensions or 26 dimensions, or 10 and 26 at the same time, which was even more confusing to me. It didn't really make geometrical sense. Now, there have ways of dealing with this in string theory, but it's not very natural, and it doesn't really fit in with the geometry of space-time in a nice way. So I never, after the dimensionality became too big, I gave up on the subject, although I was quite attractive to the original ideas of it, but not after it became 10 and 26 dimensions at the same time, and now 11. It all seems to me not focused directly on the space we live in. The space we live in has 3 space and 1 time dimension. And it's 4-dimensional with that particular signature. See, 1 and 3. That's important too, because the twistor theory relates very specifically to space-time with 1 time and 3 space. And the way it works, I should say there are variants of twistor theory, because after developing some of these ideas, the mathematicians picked up. Actually, interestingly, because they supplied some useful ideas in the twistor, particularly Michael Atiyah, who was a friend of mine, and we were in the same institute in Oxford for a while. And I learnt a lot of the mathematics that is needed for twistor theory. Some of these ideas which involve a quality known as cohomology. And cohomology is very necessary as part of twistor theory if you want to describe fields like electromagnetism. If you want to describe the Maxwell field in twistor theory, you have to bring in this mathematical notion of cohomology, which fits in very beautifully with twistor theory. And so I needed this input from the mathematicians, particularly Michael Atiyah. And then the mathematicians picked up on some of these ideas in twistor theory, how you describe nonlinear fields and things like this. This became a sizable subject within mathematics. And so it's developed in certain directions which are not exactly the same. I should say there are certain differences. I'm not quite sure how to say this. You see, it depends on the geometry of space-time. It has what's called a Minkowskian signature. So you have one time and three space. So it's not just like a four-dimensional space-time. It's very specific to one time and three space. And the twistors work very naturally in that framework. Now, if you're just doing pure mathematics, as the mathematicians are, then they like to have it four space dimensions, all four, you see. They don't like one and three. They like them to be...
You just say, I hope that this is true about the twistor story. We have no proof that that's the theory in the nature. I can give you an example. Maybe that's the answer for that question.
Yes.
Professor Maciej Dunajski, a Polish scientist from University of Cambridge,
Yes,
who works on the theory of twistors,
yes,
wrote to me a few days ago this email. In the last few months, I have been most scientifically involved in the so-called twistor theory, in which a breakthrough has occurred. We had a program on this topic in Cambridge in September, and Roger Penrose came in person. It seems that the almost 60 years old idea of unifying the theory of gravity and quantum theory may have a positive solution in this theory.
yes. Well, I've worked with Maciej Dunajski for quite a long time, and he's a very skillful mathematician who understands about twistor theory very much. I think the thing specific, you see, twistor theory is very specific to space-time geometry. It's, you see, if you take the formalism of general relativity, it depends on Riemannian, or what you call pseudo-Riemannian geometry. The pseudo means that you've got only one time and three space, so it's not really Riemannian geometry. Riemannian geometry is when you have four space dimensions, but it's curved. And Einstein needed this theory to develop general relativity. It was absolutely, he couldn't have done it otherwise. And he had to have a mathematician to help him to learn the needed geometry, differential geometry, well, Riemannian geometry, which is the geometry of curved spaces of any dimension. And it's very specific, it's not any dimension, because the general relativity theory requires four dimensions. And it's not ordinary Riemannian geometry, because it has one time and three space. So it's what people call pseudo-Riemannian geometry. Now, twistor theory is very geared. When I say twistor theory, I mean what I mean by the kind of twistor theory that I work on, and which is geared to looking at physics. The mathematicians have picked up on twistor theory very much, and they have a different version of twistor theory, where instead of having one time and three space, it's though you have four space dimensions. And that's a different kind of twistor theory. It's what I'm calling pseudo-twistor theory, if you like, because if you like, the kind of geometry which is useful for general relativity is pseudo-Riemannian geometry. It's not, the signature is different. The number of pluses and minuses you have. See, in ordinary distance, Riemannian distance or Euclidean distance, if you have a triangle, well, if you want, in ordinary coordinates, you want the distance between 2 points. It's the sum of squares. You take the square root of the sum of squares. But in Minkowski geometry, this was the idea that was introduced by Minkowski in order to understand special relativity. when Einstein first heard about it, he didn't like it at all. It was quite ironic. But later on, it was crucial to his development of general relativity. Because, you see, Minkowski geometry has 1 time and 3 space. It's very specific to that kind of geometry. And that's what special relativity depends upon. And when Einstein got finally converted to Minkowski's ideas, he realized that that's what you need to make that kind of geometry curved, and then you talk about gravity. So the gravity is incorporated into the theory once your Minkowski space is not so much Minkowski anymore, but it's curved in this way, which describes the gravity.
This is right, that the twistors theory can unify the gravity theory and quantum theory.
Well, you see, it may be, I'm not sure what Maciek was saying in the comment he was making there, but you see, there is a development of twistor theory, which I call by-twistors. There's a certain irony about all this. Let me explain the irony. When I was originally starting on this,
60 years ago.
This was in 1962.
Almost 60 years, more
Yes.
than 60 years ago.
Yes, more than 10 years.
More.
1962. When I was thinking about the positive and negative frequency problem. And that was the initial motivation. But then a little later, when I started to work out Maxwell equations and the fields and all that, it became, we were talking about positive and negative frequency. Sorry, positive and negative helicity. So that's your photon spins right-handed or left-handed, see? And that are the 2 kinds of spin you have. And the 2 halves of twistor space became more connected with helicity, right-handed or left-handed, than frequency, which is positive or negative. And this led to what I call the fundamental confusion of twistor theory. Because when I started to develop curved twistor theory to try and fit in with general relativity, I produced a thing which I call the nonlinear graviton. This was the first time that curved twistor theory came in. And it did make a curved twistor space. And when you make the curved twistor space, you can incorporate the spin of a graviton. So a graviton would be the gravitational particle, like the photon describes the particle for electromagnetic field. When you quantize it, the light becomes particular, if you like, particle-like. As we know, photons have this particle characteristic and they have the wave characteristic, and quantum theory is needed to bring these things together. And the idea is that general relativity, which talks about gravity, should have the same sort of character. You have the particle form of gravity, which would be gravitons, and the wave form, which would be gravitational fields, as we understand them. Well, nobody has observed a graviton, because the energies would be all difficult to observe directly. So that's part of what one might call quantizing gravity. So the quantum theory of gravity would involve making the gravitational field consistent with a kind of graviton picture of gravity. Now this particular solution I found, well, it wasn't a particular solution, it's a class of solutions which describe gravitons in accordance with general relativity. So they are curved, they're not flat. They're actually curved spaces, but they involve this fundamental confusion of twistor theory. The helicity and the frequency become mixed together. So to describe that, the graviton should have positive frequency. The graviton, a proper graviton should have positive frequency. But when you try to do it with twistor theory, it has positive helicity at the same time. So these 2 ideas get joined up together, and they only sort of half describe the quantized gravitational structure. So they only half describe when I say only half describe, they only describe half of the gravitons. Those are the ones which spin, I think it's left-handed, yes. not right. It depends on your conventions, you see. And this was a very puzzling situation. It came about because of this confusion, which is inherent in twistor theory as it started. The confusion was the positive frequency and the positive helicity. And they are both together in twistor theory. Now you can separate them if you take what you call dual twistors. Now you can take the twistor space or the dual twistor space. Now the dual twistor space is very similar to twistor space, but it's the other way around. So instead of the positive frequency being the positive helicity, I forget whether it's positive or negative now, negative helicity, it's the other way around for the dual ones. So the idea I had and described in the Cambridge conference is how you fit these two ideas together. And you make a structure which I refer to as by-twistors. You have to have them, instead of being a four complex dimensional space, as twistor theory is, ordinary twistor theory involves four complex dimensions, but you might want to make it three complex dimensions when you talk about projective space, rather than the vector space. The projective space, that's a mathematical concept which is like projective geometry, you see. But the projective geometry, when it's complex projective geometry, this is the six-dimensional space where each real dimension becomes complex.
Is there any connection between twistor theory and quantum teleportation?
I think I would worry about the term. When people use the word teleportation, are they talking about traveling backwards in time or something? No, I would say that's not a nice idea in this scheme.
Do you remember the moment in your history in 1962 when you developed twistor theory?
Yes, that was the first time, yes. You see, it was this notion of explaining the positive, negative frequencies in a geometrical way. And you have the splitting of the space into two halves. It's like in the complex plane, you have the real line, and it goes, one's the positive frequency, they go one way, and the negative frequency go the other way. Here you have the real space of light rays, that's five-dimensional, and then that's the space in the middle, which is five-dimensional, and that five-dimensional space, those are the null twistors. I call them null because they have zero helicity. Now, when you give them helicity, they expend, one helicity goes up and the other helicity goes down. It's these two halves.
Can we say that twistor theory is advanced mathematical approach to physics?
Well, it's very much a mathematical approach to physics, yes. You see, for a long time it's very limited in the sense that it really only talked about massless fields. Mm-hmm. You could say Maxwell's equations, maybe gravity, as I say, the nonlinear graviton is just talking about gravity. So it becomes nonlinear, as you need for general relativity, because general relativity is not a linear theory. A linear theory, Maxwell's equations are linear. That means it's much easier to handle mathematically, because you have one solution and another solution. You can add them together and produce a third solution. You can't do that if it's nonlinear. If it's nonlinear, it's more complicated. General relativity is very much a nonlinear theory. So it's very difficult to describe in these terms. However, in this picture of the nonlinear graviton, I think it's a left-handed graviton. But you can't do the right-handed one. And I used to call this the googly problem. The googly problem is not really understood except by people, except by people in the old British Empire, because it's a cricket term, you see. And it talks about a ball which spins the wrong way.
Right. From all your theories, from human consciousness, you try to answer the question how human consciousness was born, through the questions about black hole, twistor story is the most important for you?
It's the most developed, yes. You see, The consciousness thing is an idea.
I thought that the most developed
Yes.
are that connected with black hole.
No, twistor theory is much more developed as a subject. I mean, the black holes are more direct because we have evidence for them. They're there. And I guess that's what the Nobel Prize was for.
Yeah.
So the black holes...
Because we have pictures.
Yes,
Pictures.
and they are an important part of physics, quite clearly. But they sort of fit in with twistor. You see, the missing thing in twistor theory had been, and I think it needs more development, the missing theory is how you combine twistor theory with general relativity, with proper curved space-times. And you could do it partially by confusing the spin with the helicity. And so these describe left-handed gravitons. Now you want to have both left-handed and right-handed to make a proper theory of the quantum gravitational field, if you like. So you need both handedness. And the idea which I developed only rather recently, over the last few years, and I wrote a paper in honor of C.N. Yang, who was becoming 100 years old. He is 100. He's 102 or something like that, I think. And he was very famous for developing the theory of weak interactions with Lie, so Yang and Lie. And it's the important part of that theory is it's handed. You see, left-handed and right-handed are not the same. And weak interactions, apparently unique amongst physical theories, are not left-right symmetrical. See, most of physics is left-right symmetrical. If you have the theory, it describes left-handed, it's right-handed, it describes left-handed at the same time. So this applies to almost all physics. However, the weak interactions, that's not true. And they have a handedness. And Yang and Lie got the Nobel Prize for developing this theory of weak interactions, which involves a handedness. Now, the article I wrote for Yang's 100th birthday was developing, if you like, the theory. It's going the other way, you see. It's quite ironic in a way because it's making twistor theory not handed. You see, twistor theory was very much a sort of left-handed theory, if you like. And the graviton comes out as being necessarily left-handed. But you don't want that to describe gravity because it's not a left-handed theory. It's a theory which involves both left and right. So what you do in my later what I was describing in Cambridge was this idea, how you take the normal twistor theory, which, if you like, is left-handed, and you take dual twistor theory, which is right-handed. But that's just changing a sign. It's not doing anything clever. You can have these two theories. But what you do is you bring them together. And the important thing when you bring them together is that it brings quantum mechanics in. You see, if you stick with one side or the other, then the twistor theory is not quantum mechanical. It's classical, really. But when you put the two sides together, it's like, how would I put it? It's like position and momentum. See, in quantum mechanics, position and momentum are what are called canonical conjugates. So position, if you have a state of a particle which is well defined in its position, then it's completely undefined in its momentum. And the other way around. If it's well defined in its momentum, then it's completely undefined in its position. And most things are sort of in between. So they're fairly well defined position and fairly well defined momentum. But these notions are called conjugate, the canonical conjugates. And you have in quantum theory, this is the Heisenberg idea, which really started off quantum mechanics. You have these things which do not commute. AB is not equal to BA. So if you have if you work just with position, then AB is equal to BA. If you work just with momentum, then AB is equal to BA. But if you want to have position and momentum together, then AB minus BA is the other one. So you have to bring them together. So that the way the mathematics works is that what's called the commutator, that's to say, why isn't AB equal by BA? Well, you look at the difference between AB and BA, and it involves the other thing. So if you do this for position, then you get momentum. And you do it for momentum, you get position. And this is the sort of fundamental thing in quantum mechanics. Now that idea comes into twistor theory. And it comes in that the twistors, what's the canonical conjugate of twistors? It's the dual twistors. So you have the twistors and the dual twistors, and one of them is the canonical conjugate of the other, and the other is the canonical conjugate of the one. So that when you do it with quantum theory, and AB is not equal to BA, but AB minus BA involves the other thing, and the AB minus BA, the other thing, involves the one thing. These are the conjugate variables. Now in crystal theory, the conjugate variables are twistors and the dual twistors. So those are conjugate to each other. Now you make an algebra which involves both twistors and the dual twistors. And when you make that algebra, it has quite curious implications, which might seem to involve things like particle physics. I think that hasn't been developed, I should say. That's only an idea. But I think there's a reasonable chance that the ideas that, well, when it talks about strong interactions, that's the interactions which hold particles together. Or
which are the most fundamental questions we can find when we ever confirm Twistor's theory in all details?
Well, it's as a mathematical theory, it doesn't need confirmation. It's just a theory. It's just a mathematical structure. But the question is when it fits in with physics.
If we
yes.
ever confirm that this mathematical concept exists in the nature.
Yes. No, I think that's, well, it's
Physical
a little
rule.
difficult to formulate that. Because when would you know? You see, I think it could be, I'm talking now about things which haven't been developed, so I'm speculating now.
Yep.
This is speculation. Okay. Now, I think it's quite possible that these by-twistors, which do involve both the twistors and the dual twistors, so you are enabled to talk about left-handed and right-handed together. And I think they would enable you to talk about general relativity together. This is still not achieved yet, but I think there are good indications that this could be done. Now, could it go beyond that and talk about how the quantum aspects of general relativity are brought out? This is speculation. I don't know. Does it fit in with particle physics? Up to this point, it doesn't. I remember I had an idea about how to make particle physics fit in with twistor theory. And I remember I was visiting Caltech at one point, and I think Stephen Hawking was there, and he arranged a meeting between me and Richard Feynman. And I talked about twistors to Richard Feynman. And I asked him about some ideas I had about particle physics. And he was very good. He said, don't follow that. That's not going to be useful. But do follow what you're doing on twistor theory. He thought that was a good idea. So I give him credit, because the particular idea I was looking at for particle physics was probably completely wrong. And he was noticing that it was not a fruitful idea. So far, particle physics has not really fitted in with twistor theory. Now, I think there is a reasonable chance that it would fit in with by-twistor theory. The reason I'm saying this initially, this is speculation. I don't know to what extent this is correct. But the theory of strong interactions, you see, in particle physics you have weak interactions, that's the Yang and Lee business, which I mentioned before, which have a handedness to them.
Yes.
And there are gravitational interactions, which don't really form part of normal particle physics. And you've got these strong interactions. Now the strong interactions are strong because they dwarf everything else.
Yep.
And they hold the particles together, if you like. They're the main thing which dominates the particle physics. Now, how do they fit in with twistor theory? Well, they might do, because of when you do the by-twistors and you look at the way that the twistors and by-twistors fit together, you find there is a very nice kind of triple product. How to explain this? It's a bit like, see, when you go back to Hamilton, Hamilton was a very distinguished mathematical physicist, and many of the ideas become important in physics, Hamiltonians and things like this. But what excited him the most was his discovery of quaternions. This was a kind of algebra which you could, you see, rather than the complex numbers, which describe, one space of time, it's only a two-dimensional space. The quaternions talk about a three-dimensional space. But the key thing about it is that AB is not equal to BA. And he formed this algebra, which is called quaternions. And this quaternionic algebra, Hamilton got very sold on it, and he spent the rest of his life, many people say he wasted the rest of his life on developing a theory of quaternions. Now, it's a bit mixed story, this, you see. But very shortly after Hamilton discovered his quaternions, other people, I think there were about 3 mathematicians independently, saw how to develop this idea into what are called Octonions. Mm-hmm. And these are not just 4-dimensional structures, they're 8-dimensional. And you see, Hamilton's quaternions have AB is not equal to BA. The Octonions have a more complicated thing, that A times B times C is not the same as A times B times C. So it depends where you put the bracket. AB times C is not the same as A times BC. So it's a little more complicated piece of...
But today we know that it's not true.
You see, it's not true in the Octonian algebra. You see, the quaternions, it is true. Mm-hmm. So the Octonians, it's not true. Now, I had a phase of thinking, I wonder whether Octonians in the split form, you see, again, it's the signature question. Do you have 3 pluses and 1 minus in space-time? Now, there is another version of Octonians, which is called split Octonians. And those, instead of having all pluses, normal Octonians have 8 pluses, there's 7 pluses because it's 8 things which are added together. And that's the structure which it's developed on. But there's a special kind of Octonians called split Octonians, where you have 4 pluses and 4 minuses. And I often wondered whether this had anything to do with twistor theory. And what I finally realized is it does have something to do with the by-twistor theory. That the by-twistor theory, you can construct the Octonions, or the split Octonions. So it really is connected with the split Octonions. And the question is, do these split Octonions have anything to do with particle physics? I think they may well do, mainly because in this construction of the split Octonions, you have you have a triple, you see, how to say this? See, the quaternions involved a thing which is called a vector product. Mm-hmm. You have the scalar part and the vector part. And when you multiply the vectors together, you do this with this construction of what's called the cross product. So you have 2 vectors and you produce another vector at right angles to the 2. So you have 2 in space, in ordinary 3 space. 2, 1 there, and then the product points perpendicular to the plane of the 2. But AB is not the same as BA. So you have this Hamiltonian structure for the quaternions, that AB is not BA. But ABC is still the same as a BC. A, B, C. You see what I mean? But the Octonions go one step beyond that, and you have an 8-dimensional structure where this algebra for ABC, well, AB times C, is not the same as A times BC.
When I'm hearing you now, I think that the abstractional thinking is the never-ending story.
Well, it's I hope never-ending. You see, it does end in a certain sense, because there are certain theorems. If you have the associative rule, which is ABC, well, then you stick at 4 dimensions. And if you have the Octonian rule with the what they call the alternative rule, which is another algebraic structure, but AB times C is not the same as A times BC. You have these Octonians, but you stuck there. That's the end. You see, you might say it's an unending story. In a certain sense, it is, because you can talk about groups and they get bigger and bigger and it gets huge, you see. But if you want about these algebras, they do stop. And they stop at the Octonians. And this may well be, you see, particle physics really stops at a certain point. It doesn't keep on going. The space-time structure only stops at a certain point. You've only got 3 space and 1 time. So it's not as though physics is more, I mean, it doesn't, how do I put this? See, mathematically, you can go endlessly complicated. But physics is only interested in certain aspects of mathematics.
Yeah. If something exists in the nature.
Yes, that's right.